Question 16 says, a light rigid rod of length L having a point mass m at its one end is made to accelerate vertically upward with constant acceleration g. At t equal to 0, point mass is given horizontal velocity v0 equal to root 10 gl. If Ti, Vi in SI unit denotes tension in rod and velocity of point mass respect to rod and P at point I, then match the column 1 with column 2. The values of m, L, G are given. M is 1 kg, L is 1 meter, G is 10 meter per second squared. This is the figure and these are the columns. So let's first find the value of TA. Well, this point is given acceleration G. So if we fix our reference frame at this point, which is accelerating upward with acceleration G, we can apply the work energy theorem, but we will have to also consider work done by the pseudo force. That is for finding speeds at other points, right? At point A itself, if we draw the FBD, there is of course mg, its weight, and the pseudo force, which is also mg, and there is tension TA here, and acceleration with respect to this frame is v0 square by L in this direction, right? A is equal to v0 square by L. So equation is TA minus 2mg is equal to m VA square by L, that means m into 10g, and that gives us the value of TA as 12 mg. If we put the values of m and g, it is 120 Newton, and so of course 120 is there, so that means A matches with R clearly, and well, obviously tension will be the highest when the particle is at point A, right? It's very clear from this equation, because at other points one relative speed will be less because of the work energy theorem that we employ, and also the direction of mg in this particular case and direction of tension are opposites. So for these two reasons, we can also say that tension at A is highest among all the points. So that means A also matches with T. Let's look at TB now. For finding TB, we also need to find VB, and for finding VB, we apply work energy theorem, and we apply work energy theorem. So we get work done by mg and work done by pseudo force, that will be equal to minus 2 mgl in the reference frame of point P, and this is equal to change in kinetic energy, so which is final kinetic energy, that means half m VB square minus half m, initial speed was root 10 gl, so it is 10 gl, and well, let's simplify this. This gives us the value of VB square as equal to 6 gl, or VB itself will be under root 60 meter per second. That means C matches with, well, D matches with S, and it's obviously not the maximum on all other points. Now that we have VB, we can find TB, and TB will be then at this point. If you look at the FBD, so there is 2 mg, one for pseudo force and one for weight, and tension is in this direction, TB. So TB will be m VB square by L, and if you put the values, it is m 6gl square by L, that means 6 mg, and this is 60 Newton. So that means B matches with P. So B is matching with P. Let's find VC now. Well, if you find VC, the work done by the gravitational force and the pseudo force will be minus 4 mgl. Let me put the value of TB that we just found is 6 mg, in fact 60 Newton. Coming to VC, so we have the equation minus 4 mgl by applying work energy theorem is equal to half m VC square minus half m 10 gl, and Vc square then will be equal to 2gl. So Vc itself is root 20 units. That means C matches with Q, and well, only A will match with T, others will not match. So that means this is our answer. Our answer should be then A matches with R and T, B matches with P, C matches with Q, and D matches with S. Let's now go to the next question. Well, now we are into question 17, which says a block of mass M equal to 10 kg is hanging vertically by help of 3 elastic wires 1, 2 and 3 as shown. Young's modulus Y, cross-sectional area A and length L are shown. If delta Li in meter is the elongation in wire I and delta Ui in J is the elastic potential energy stored in wire I, then match the following. Given Ya by L equals 1000 in SI unit, delta Li is in meter and delta Ui is in joule. This is the diagram given to us. There are 3 wires. So in column 1 we have entries like delta L1, delta U1, delta L3, delta U3. So obviously the question is from the topic elasticity, and the entries on the left basically are for elongation and elastic potential energy stored. So now there are 3 wires. So first of all we find tension in each wire, and we can see that in wire 3 tension will be simply equal to weight of the block. So we can say that T3, tension in wire 3, is mg, and that is equal to 10 into G, which is, let's say, 100 Newton. Now to find tension in other 2 wires, we take FBD of the junction, let's call the junction O, and if I look at O, there is force T3, which is 100 Newton, and this is the horizontal line, this is T2, and this angle is 30 degree. Similarly, this is T1, and this angle is also 30 degree. So T3 we already know, it's 100 Newton, and if we resolve forces along horizontal and vertical directions, we can see that T1 cos 30 degree is equal to T2 cos 30 degree. That means T1 equals T2, and in vertically 2 T1 sin 30 degree is equal to T3 then. So that means 2 T1 sin 30 degree is equal to T3, which means T1 is equal to T2 is equal to T3, and each one is 100 Newton. So that result we have now. Let's start finding delta L1. Now the expression for delta L in general will be force into original length divided by A into Young's modulus. A is the area of cross section. So for delta L1, if I apply the formula, F is same everywhere, and that is 100 Newton, so it's 100. Length of wire 1 is L, so let's put it as L. Area of cross section, let's say, is A, it's given in fact A, and Young's modulus is Y. Now we have been given Ya by L is 1000 units. So that means delta L1 is equal to 100 by 1000, or simply 0.1 meter. So we can see that delta L1, A matches with Q then, right? A matches with Q, and one of the entries in column 2 is same as in other 2 wires. So let's also find delta L2 and delta L3 to check whether this also matches. So if I find delta L2, force is same. In fact, the 2 wires are identical, same Young's modulus, same length and same area of cross section, and tension also is same. So delta L2 obviously is equal to delta L1, that is equal to 0.1. Let's now find delta L3, and that is equal to tension again is same, 100 Newton divided by A is A only. Young's modulus here is 2y, but the length also is 2L, and we see that this is also equal to in fact 0.1 meter. So this is also 0.1 meter, right? So that means A matches with Q as well as S, and same goes for C. Delta L3 is also matching with Q and S. Let's look at the expression for elastic potential energy stored. Elastic potential energy stored in general, delta U will be half into stress, which is T by A, into strain, which is T by A into Y, into volume, and volume is area of cross section into length. Well, area of cross section is same for all the cases, but length is not same for all the cases. So let's write as L, okay, into area of cross section, which is same for all. Now, if we look at delta U1, it is 1 by 2 T square divided by AY into L. Now, A is same in all the cases, but L and Y may be different. The delta U1, Y is Y, and capital L is simply small l, right? So, if we calculate the value, delta U1, it is T square will become 10 to the power 4. Of course, 2 is here. And YA by L will be 1000 units. So, that means here it is 1000. It is 10 by 2 or 5 units. So, delta U1 is 5 units. What about delta U2 and U3? Let's first find delta U3. You see that for 3, Y is 2Y and L is 2L. So, that means it is same. So, this is also equal to delta U1, and that is 5 units. Delta U2 will be same anyway as delta U1 because the wires are identical and same tension. So, it's also 5 units. So, that means B will match with R and S, and D will also match with R and S. So, this is our matrix match. A matches with QS, B matches with RS, C matches with QS, and D matches with RS. Well, let's go to the next question now.